Hello everyone. We are now going to begin our lecture on section 3 of chapter 3, which is on truth tables for the conditional and biconditional. We've already learned how to construct truth tables for conjunctions, disjunctions, as well as negations. So this time we are going to look at the truth tables for two more logic concepts, which is conditional and biconditional. And recall that conditional statements are if-then statements and biconditional statements are if and only if statements. We'll work through some examples of these as well once we learn how to construct the truth tables, and then we will go into three other logic concepts called self-contradictions, tautology, and implications. So once again, here are the topics we will learn in this section. First, we learn how to construct truth tables involving conditional statements. Then we'll go into constructing truth tables involving biconditional statements. And then we will understand what self-contradictions are, tautologies are, and implications are. And all those will be explained using truth tables as well. So let's look at the truth table for conditionals. Recall that the symbol for conditional is a one-directional arrow, right? And the way it reads is we have, and let me redo this 1 second here. So we have a one-directional arrow. On the left side of the arrow would be a P statement, and then on the right side will be the Q statement, and it reads as if the condition P is met, then it'll result in Q. All right, so that's how we read it. So the first one is called the antecedent, and then the one that comes after the arrow, the Q, will be the result or the consequent. All right. Now, let's go through the table here. There are again 4 cases, and we set up the cases, the combinations, all possible combinations of true and false that P and Q could take. So T, true, 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 false, false, true, and false, false. And let's see how it resolves using the conditional. So true and true resolves to a true. True and false resolves to a false. False and true resolves to a true, and false resolves to a true. All right, so we have to just know this table, and then it says the conditional statement P and then the arrow followed by a Q is true in every case except when P is a true statement. Except when P is a true statement and Q is a false statement. So the only place when the conditional will resolve to a false is when P is true and Q is false. All right, otherwise it's always true. So let me give you a quick example to make it a little more meaningful for you. Think of the P is as a statement saying if you get an A. If you get an A in the class, then Q will be I will give you a prize. I will give a prize. All right, so the conditional statement is if you get an A in the course, then I will give you a prize. So if P, so P is getting an A and Q is me giving you a prize, right? So if you do well in the test, or if you do well in the course, if you get an A, that is, and I give you a prize, then you've met the condition, I've given you a prize, I've kept my promise, so it's true. All right, that's why it's true. In the second case, if you get an A but I don't give you the prize, what has happened? You have met the condition, but I didn't keep my promise. I didn't give you the prize even though you got an A, and that's what makes the conditional false. All right. For case 3, which is slightly tricky, let's understand this. If P is false, that means you did not get an A, but Q is T. I still gave you a prize. All right. I kept my promise. All right, well, even though you didn't meet the condition, I still gave you the prize. Maybe I gave you the benefit of the doubt. Maybe I wanted to encourage you to do better the next time. It's true, I still gave you the prize. That resolves to a T. That resolves to a true. All right, so it essentially depends on that me fulfilling the my promise. All right, or Q being met. And case 4 is you didn't get an A. I didn't give you the prize as it should have been. It resolves to a true condition. All right. So hopefully this example gives more meaning to the conditional truth table. All right. So now let's go on to the next slide to see what more there is. We are now going to go through an example of creating a truth table for the conditional statement. The statement given to us is not P, and then we have a not Q as well, and between them we have the conditional symbol. So this reads as if not P, then not Q. All right, so the process is the same as we worked previously with conjunctions, disjunctions, or negations, but this time we have to use the truth table for the conditional, the truth values for the conditional. So we start by first listing all the P and Q values, all possible cases, all possible combinations of true and false for P and Q. So for the P, it would be, for the first case rather, it would be true, true. Then the next one would be true, false, and then it would be false, true, and then finally false, false. All right. So that's P and Q, the first two columns. Then we are going to set up this statement given to us, which is not P. So in the third column, I'm going to write not P, followed by the conditional symbol, this arrow, and then followed by the not Q. So under not P, I'm going to negate all the truth values for P. So the trues becomes falses and the false becomes true. All right, the false becomes true. So let's start with the first one. This true will become a false. This is a false. Then the next true also becomes a false. The F becomes a T and then also a T. Now we go on to negating all the Q values. All right. Once we complete the negation, then we will work out the truth values using the conditional, and those will be listed under the arrow. All right, so we have a true to start with for the Q, so that will become a false. Correct? So let's write false, and then we have a false which will become a true. Then we have a T which will become an F, and the F will become a T. All right, and then we start the evaluation of the conditional. So F and F, if both are false, then it is a true. Correct? So I'm going to write a true. It's a true. Now, F and T is also a true. F and T is also a true. Then T and F, if P is T, true, and Q is a false, that is the only time where it'll resolve to a false. All right, so let's write the false. And then when both are true, then it is also true. Correct? So we got the final result here of the conditional of this statement. So let me highlight this. All right, so if not P, then not Q has truth values which are T, T, F, T for the following values of not P and not Q. All right. So here's the solution for the same statement, for the same conditional statement that we worked previously. So let's just pull up the answer. They have followed the same process. They've listed all the combinations of true and false for P and Q, and then you'll see they have negated all the P values, which is going to be step 1. Then they'll go and negate the Q values, which is going to be step 2, and then they will evaluate the conditional. All right, so let's see if they came up with the same answer. So step 1, and then all the values for not P comes up for the different combinations. T for P is an F, T for P is an F, F becomes a T, and then another F becomes a T. And then they go on to step 2, which is negating all the Q values, and that would be FT, FT. All right, and then finally they will evaluate the conditional, which is going to be step 3. So T, T, F, T. All right. So that's the final answer. It's a conditional. The answer lies under the final answer rather, right, lies under the arrow for the conditional, the unidirectional arrow. Now we'll talk about the biconditional statement, and then we will construct a table, a truth table for the biconditional. All right, as you can see, the truth table is rather elaborate, but we will go through it step by step, break it up into parts. All right, but let's first consider what biconditional is. Biconditional reads as if and only if. If and only if. Now, as the word biconditional suggests, it refers to two conditions. All right, bi means two, correct? So conditional suggests there are two conditions, and that is exactly what it is. All right, so the notation for biconditional is written as P and then a bidirectional arrow, so to speak, all right, and then Q. And the two conditions are listed like this. If P, then Q, and if Q, then P. All right, so this bidirectional arrow suggests that if P, then Q, and then you go the other way around, if Q, then P. So when we work on the truth table, you will see that we will have to first evaluate the two conditions separately, and then we have to take the conjunction or the and of both the conditions here. All right, so let's go through this table. It works the same process. They follow the same process. They first listed all the possible true and false combinations of P and Q. So we have TT, TF, FT, FF, the four conditions. And then we have the first condition, which is if P, then Q, and then over the next three columns. So they've listed all the same truth values for P over here. Just copied the same values here. And then in step 2, these are the different steps below. So in step 2, they just list the values for Q, and then they resolve the condition. They evaluate the conditionals. So in the conditional, remember, if the if condition, when the if condition is true, but the then condition is a false, that's the only time when it resolves to a false. All right, otherwise it's always true. So let's see what the resolution is here. So true gives a true, true, false, that's the only time it resolves to a false. Then FT is a true, and again FF is a true. So that's step 3, which is the resolution of if P then Q. So I'm going to just highlight this, all right, because eventually we're going to work with this. We need this, right? Now we go to the next part of the condition, or the next condition, all right, this condition. Again, works the same way, but this time we have the Q values listed first and then the P values, and then we resolve the conditional. All right, so again, same thing. When the if condition is true, but the then condition is false, that's the only time when it resolves to a false. Otherwise, it'll always be a true. So true, true is a true. False, true, false, true is a true. And then true, false is a false, right? This is the only place when it will resolve to a false, and then FF, false, false, resolves to a true. And that's step 6. So I'm going to highlight this because now we are going to take the AND, or the conjunction of these two columns of the truth values in these two columns under the arrows. All right. So, but this time we are evaluating AND, conjunction. So we have to use the truth table for the conjunction. All right. So let's go through this first. In the conjunction here, we have TT gives a T, FT resolves to an F, TF resolves to an F, and then TT resolves to a T. All right, so for the if and only if statement, the final truth table values are T, F, F, T. All right. So the truth values for the biconditional statement, if and only if P then Q, is true only when P and Q have the same truth value, that is, when both are true or both are false. So if when we had these when we had our P and Q values, when we listed them as true, 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 false, false, true, and false, false, all right, so the if and only if P, if and only if P then Q would resolve to a true and then a false, false, true. So that means that when both P and Q have the same truth values, whether they are both true or both false, the resolution will be a true. If one is a true, the other one is a false, then it'll resolve to a false. That's what they are saying here. All right. So now let's go through an example to create a truth table for a statement which has not only the biconditional but also the conditional as well as some of the other logic operators. All right, so let's first go through the statement in symbolic form and then we'll try to put it in words. All right, so here we see there's a not P, negation, so not P, and then we have the biconditional symbol followed by, within brackets, we have not Q, then the conditional statement followed by R. Correct? So in words, this would read as if and only if not P, then if not Q, then R. Correct? So we are going to go and construct a truth table for it in the next slide, and we'll go through it again step by step. So here we have the entire table where we are going to work on the example of the statement that was given to us. But before that, I'm going to remind you of the truth values for the biconditional and the conditional. So recall that based on the sequence of the four cases for P and Q, the biconditional truth values occur like this. The first one is a true, correct? The first one is a true. Then we have a false, followed by a false, followed by a true. So, which means that for the biconditional, when both P and Q, both statements are true, it's a true. Or when both statements are false, that's also a true. However, if any one of the statements are false, or any one of the statements is false, then the result is a false. All right. As far as the conditional statement is concerned, it goes like this. It's true followed by a true first case 2, and then the third case is a false, the fourth case is a true. So for the conditional, only when the if condition is true but the then condition is a false, we get a false for a truth value. All right, otherwise all other cases are true, correct? So given that, let's proceed to completing this table. Again, I'm going to pull up the results and it's going to show up one by one at a time. But over here we have three statements, P, Q, and R. So that's why you see three columns to start with, and then we have the columns for the different parts of the statement for which we are creating the truth value. So we have the not P first, followed by the biconditional, and then within brackets we have not Q, and then the conditional followed by R. Now we are told that we should work on the brackets, whatever is within the brackets first, which is how it should be. But for this example, they are going to work on not P first. So this is really step 4 if we follow the order of operation, so to speak, but this will come up first. All right, that's how this slide was created. So let's pull up the values here. So over here you see this is step 4, and then not P means negating all the P values, correct? So all the T's would become an F and F's would become T's. All right, so let's go there. All right, so one at a time. F, 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 and then it should be T, 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 and T. All right. Now we will go on to working on what is within the brackets. So not Q. So this time for the Q values, we have to negate them. So all the T's would become F's and all the F's would become T's, correct? So let's pull up those values, and that would be step 1. You see over here at the bottom, number 1 came up, so that's really step 1. So let's see, it should be F, F, T, T, F, F, and then T, 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 T. All right. Then we will have to go to step 2, which is really R. All right. So let's see. And for R, there's no negation. So we are just going to write the values of R over here under R. All right. So there's no negation there. So that's step 2. Let's pull up the values TF, 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 and TF. All right. TF, TF. Exactly the same values that you see in the third column. So now we will go ahead and evaluate the conditionals. All right. So conditionals, remember, only when we have a true for the first statement for the if statement, but a false for the then statement, we will have false. Otherwise, everything else should be a true. All right, so let's pull up the values here. This is going to be step 3. So FT should be a T. All right, it should be a T. FF should be a T. TT should be a T. TF should be F. All right. TF should be F, FT should be T, FF should be T, TT should be T, and TF should be F. All right. So let me just highlight this row. All right. Let's highlight this row. And then we will now have to evaluate the biconditional, which is going to be the fifth step. But which values are we comparing over here to come up with the values of the biconditional? It's the not P and what I've highlighted here. All right, so let's highlight this as well. Just a second. All right, this is what we are, these two columns are what we are considering to evaluate the biconditional. So let's pull it up here one by one. So for the biconditional, recall over here, we have TFFT. All right. So as long as both are true or both are false, we should get a true. Otherwise, it should be a false. So FT should come out as false. FT should come up as false. FT comes up as false. FF should come up as true. TT should come up as true. TT true. TT true. And then the last one should be an F. Right? So that's what we got, and this is the final result. All right? The final evaluation of the statement that we worked on. All right? Now we'll work on an application problem using real data in compound statements to come up with truth values. So it says here the graph on the next slide represents the student population by age group in 2013 for the State College of Florida. Use this graph to determine the truth value of the following compound statements. All right. So essentially in this slide, they tell us that we have to look at a pie chart given in the next slide, which represents the student population by age group, what percentage of student population at this college were within a certain age group, and then we are going to use the graph. Now we don't know what the compound statement is. Hopefully that'll also come up in the next slide or the subsequent slides. All right, so this is the graph that we were told to look at. It's actually a pie chart, and it has the percentage of students by age group. So there were 44% of the students at the college who were younger than 20, so less than 20 years old. Then we had 41% of students were in the age range of 20 to 29, 8% in the age range 30 to 39, 5% in the age range 40 to 49, and 2% of the student population was 50 or older, greater than 50. All right. So given this picture, let's look at the statement that we have to analyze next. All right. So here's a compound statement that we have to create or find the truth value of. So let's read through it first. It says if 44% of the SCF population is younger than 20 or 38% of the SCF population is age 20 to 29, then 8% of the SCF population is age 30 to 39. So while we were reading it, I noticed there were some if statements. Of course, it starts with an F. So let's try to kind of highlight these. So there's an if here, and then there is an or, I could see that, and there's a then. All right. So, of course, this is kind of, these will help us to construct the statement. All right. So it says if 44% of the SCF, so I'm going to just break this up into statements and denote them with letters. So PQR looks like we have three statements here. So we are going to have a P. All right, so P, and let's call that, sorry, and I'm going to denote P as 44%, 44% younger than 20 years. And Q, we'll denote Q as 38% in age group 20 to 29, and R will be 8%, correct? 8% in age 30 to 39. Now, given that, how do we construct the statement? So it says if P, all right, if P, or Q, right, 38% or Q, then R, correct? So we are going to write it as P or Q. So let's write that. Let me pull up a pen here, a different color maybe. All right, so we are going to write it as P, or remember what the symbol for or is. Or is V, right? So P or Q, and then the conditional statement followed by R. So that's how the statement in symbolic form is going to look like. So let's go on to the next slide to see how they have worked out the solutions and the steps that they have followed. So let's go over the step-by-step process that they have given us here to come up with the solution. They'll start with let P be 44% of the SCF population is younger than 20, and then Q is 38% of the SCF population in age 20 to 29, followed by R, 8% of the SCF population is age 30 to 39. All right, and then we have the statement put together that was shown in the previous slide. The statement given to us in symbolic form would be within brackets P or Q and then the conditional symbol followed by R. This reads as if P or Q, then R, correct? But before we go on to finding the truth value, let's find the true, whether each of these statements are true or false. All right, so based on the chart, based on the pie chart that was given to us, 44% of the population was younger than 20. That's a true statement. All right, so this was a true statement. However, the next one, Q, 38% is not a true statement. I think it was 41% according to the pie chart. It was 41% of the population that was in the age group 20 to 29. So this should be marked as a false statement. And then R, 8% in 30 to 39 was a true statement. All right, so you can go back and check the pie chart. So based on these two true, false, true values, let's evaluate the statement. So P is true, and then we have the or followed by F. So true or false should give us in an or statement, it should be a true. As long as one is true in between P or Q, it evaluates to a true. And then R is true, correct? So we are going to write true for R, and then this is the conditional, correct? So this is the conditional. So in a conditional, if both are true, all right, if both are true, then it evaluates to a true value. All right, so we will see the solution come up in the next slide, but here we have worked out, and let's see if it comes up with a true or not. So here we go. Let's pull up the values or the solution step by step. So P or Q, we said P was true, but Q was false, correct? That's what they have here. It said P and R are true, but Q was a false. So based on that, true or false should give us a true, correct? And we have a true for the R, which should result in true for the final answer. So the original statement is true, correct? Let's look at another compound statement based on the same problem. It says here 5% of the SCF population is age 40 to 49 and 5% of the SCF population is age 50 and older. If and only if 41% of the SCF population is age 20 to 29. All right. So again, we are going to first split them into separate statements, naming them P, Q, and R. We are going to call the first one P, so 5% of the SCF population is age 40 to 49. And then we are going to denote the other one with a Q. So 5% of the CF population is age 50. So let me take out my pen here. So the first one is going to be here, from here to here is going to be P, and then the next one is going to be a Q, right? And then this other one, 41% of the CF population is age 20 to 25 is going to be the R, all right? And then let's look at the logical operators. We have an AND, right? So let's take out we have an AND. So that's going to be used in our construction of the logic statement. And then we have an if and only if, right? So this is the biconditional statement. All right, so let's go on to the next slide to see how the statement is symbolically constructed. But one other thing that I want to say here is the first one, which is 5% of the SCF population is age 40 to 49, was a true statement based on the pie chart given to us. 5% of the SCF population is age 50. This one is a false statement, all right? And then 41% in age 20 to 29 should be a true statement, right? So we'll bring up the solutions now. First, we will separate the three statements and write them with P, Q, and R. So P was 5% of the SCF population is age 40 to 49, which was a true statement. And then the next one is 5% of SCF is age 50 or older. This one was a false statement. It was 2%, all right? And then R is 41% of the SCF population is age 20 to 29, which was a true statement. So how do we construct the statement in symbolic form? It should say P and Q, all right? P and Q, and then we have the biconditional statement, which is R. So, which means if and only if P and Q, then R. So that's how we read it in words. And now we come to evaluating the truth value. So we have P and Q. So we said P was a true statement, right? So P was a true statement, a true. And then we have an and Q was a false statement. And then we have the biconditional R was a true statement, correct? So we have to evaluate what is in the brackets first. For an and statement, for a conjunction, if any one of the statements is a false, then it should evaluate to a false, right? And then we have the biconditional true, and when we consider false and true with the biconditional, it should give us a false, correct? For the biconditional, both have to be true or both have to be false. So let's see what they come up with, but I will probably have to erase my writing so that we can see what is coming up next. All right, so let me remove my writing here. So P and R are true, Q is false. So given that T and F, and then we have the biconditional T. So T and F should evaluate to a false, and then biconditional with true should give us a false. So let's see what comes up. Yes, F biconditional T, which should give us an F. All right, so the original statement is evaluated to be a false statement. Now we will talk about some other logic concepts. One of them is called a self-contradiction. A self-contradiction is a compound statement that will always end up a false statement. All right, so when every truth value in the answer column of the truth table is false, then the statement is a self-contradiction. So out of those four cases, if we end up finding that all the cases end up as false, all four cases, or as many cases as there may be, end up as false, then it means it's a self-contradiction. So here's an example where we will end up with all cases resolving to a false, and which is a self-contradiction. So we have the statement here, if and only if P, then Q, and if and only if P, then not Q. All right, so let's see how this will work. Let's go through the process of creating a truth table for this. So let's go through the solution. Let's evaluate the statement that was given to us and see if we get all false statements, which will result in a self-contradiction. All right, so here we have the table set up. We have all the combinations of true and false for P and Q. So we have all the four cases in the first two columns, and then we have the statement that we will have to resolve. So the first one is if and only if then Q, and then we have the and statement followed by if and only if P, then not Q. So remember, we first have to work through the brackets first, whatever is within parentheses. So for the biconditional, the first one is a straightforward biconditional truth table evaluation, right? So in the biconditional, if both values are the same, then they are true. Otherwise, it's false. If any one of them is a false, then it's a false statement. All right. If both values are the same, then it results in a true. So TT gives us a T, TF gives us an F, FT gives us an F, FF gives us a T. All right. So that's the first step. For the second step, we go to the next statement and first list the values of P, which should be the same as what's listed in the first column. And then we work through not Q. So that's negation. We negate all the Q values in the second column. So the trues become false and the false becomes trues. All right. So once we have that FT, we will now evaluate the biconditional. Again, same logic. If any one of them is a false, then it'll result in a false. If both have the same value, it'll be true. So T and F should give us an F. T and T gives us a T. F and F gives us a T. They are the same value, even though they are false. It's the same value, therefore a true, and then F and T results in a false. All right, so that was the fourth step. So I'm going to again highlight, let's highlight these columns here, which we are going to consider to do the final evaluation. Let me see, let me pick a yellow here. All right, so this column, and then with this we are comparing this column. All right, and this time it's an and, correct? We are doing an and operation. So in the and operation, there's if any of the values is a false, it will result in a false. All right, both have to be true in order for an and statement to be true. All right, so T and F gives us an F. F and T gives us an F. F and T gives us an F. T and F gives us an F. We see all the cases result in F. And this is an example of what we call a self-contradiction. So the statement is a self-contradiction or a logically false statement. It'll never be true. Now we'll talk about another concept in logic, which is called a tautology. A tautology is a compound statement that is always true. So just like with the self-contradiction, we found that uh, all the evaluations ended up to a false. This time we'll see that all the evaluations from a particular compound statement will result in a true. All right, so when every truth value in the answer column of the truth table is true, the statement is a tautology. Now here's an example which will result in all true values in a truth table, or which will result in what's called a tautology. Let's look at the statement. It says, if P and Q, then P or R. All right, so let's construct a truth table with this statement and see if we end up with all true values. So here's the complete truth table of what's considered to be a tautology. We will see that the statement will be resolved to all true values. So let's read through this table and try to understand how they worked it out. We have three statements. Correct? We had three separate statements. So as you see, we don't have just 4 cases, we have 8 cases. So the number of cases that you will have if you work with three different statements will be 2 to the power 3. So if you have 4 statements, it'll be 2 to the power 4. So that's the formula. So the number of cases will be 2 to the power n. So here we have 3 statements. So we have 8 cases, 2 to the power 3. All right. So over here on the right hand side of the table, we have the statement that we have to evaluate P and Q within brackets, followed by the if condition, followed by P or R. So let's evaluate P and Q first. Recall that for the and, it'll be a true value only when both statements are true. Otherwise, it'll always end up being a false. So P and Q, T results in a T results in a T. Then we have T, F results in an F T results in F T results in F is an F is equal to an F. All right. P and Q, we have gone through all the cases and we came up with the result. All right. So the next one is resolving P or Q, the other bracket over here. All right. So this time we are comparing P or Q. So I'm going to highlight that, those two here, this column and this column. All right. And this is an or. For an or statement, the only time you get false is when both the statements are false. All right. So true and true. All right. True and true should result in a true. True false should result in a true. True results in true. True false results in true. False true results in true. And then we have FF, that's the time when we will get a false. Then we have FT, which is a true, and FF again should be a false. All right. And then we go to the if conditional symbol here and do the conditional evaluation. But this time we are comparing. What are we comparing here? We are comparing these values, right? We are comparing these values. And for the conditional, the only time you will get a false is when the if condition is a true, but the then condition is a false. All right. So it has to be TF to make something false. So we have TT resulting in a T, TT resulting in a T, FT results in a T, FT results in a T, FT again a T, FT, FF is a T, FT is a T, FF is a T. We do not have any cases where the first one is a T but the other one is a false. All right. So we have all true evaluations once we complete the conditional evaluation, and it shows all trues. That's what makes it a tautology. Now, one last concept that we need to learn about is an implication. An implication is a conditional statement that is a tautology. Now, a tautology is one where all the truth values resolve to a value of true for every case. But in a conditional statement, what happens is whenever the antecedent is true, the consequent will also be true. If that happens, then it is an implication. Now, recall that in a conditional statement, the if statement is the antecedent and the then statement is the consequent. All right. Now here's an example of the implication. It says here, determine whether the conditional statement, this one here, which we will go through carefully, is an implication or not. All right, so the statement given to us is a conditional statement because an implication always pertains, always relates to a conditional statement. And what is the conditional statement? We have within brackets here. Actually, there is a nested bracket, it's a bracket within the bracket. So it says P or Q. And then we have the and symbol and not Q. And then we have the conditional symbol followed by a P. So how would this read in words? All right. So since it's a conditional statement, we have to start with if. So it will read as if P or Q and not Q, then P. All right, so that is the statement. If P or Q and not Q, then P. So let's go create a truth table for it and see what this resolves to. So here we have the truth table worked out for us, but we will walk through it and see whether it is an implication or not. Again, keep in mind that in order for it to be an implication, the final truth values should all resolve to a true value. All right. So here we start again with P and Q in the first two columns and set it up with all combinations of true and false, all possible combinations of true and false. And on the other side over here for the other columns, we set up the statement given to us in columns. So remember there was nested brackets, nested parentheses involved. So within the square brackets, we had P or Q, which is going to be the first column, and then we have the and symbol, and then the not Q, the negation of Q, and then the conditional symbol followed by P. All right, so we have to work the brackets first, and then because there's a nested bracket, we have to work the nested bracket first. So that's going to be step one. And this is an or statement, all right, or operator. So in an or operator, all values will be true except when except when both the values are false. All right. So here we have true, true resolves to a true, true, false resolves to a true. Then we have false, true resolves to a true, false, false resolves to a false. All right. So that was all the OR operators, all the values obtained from the OR operator. Then we go to the next step, step 2, which is to negate the Q. So all the trues become false and all the false become true. So true, false. So negate all your Q values, then they become FT, FT. And then we have to go to the AND, the conjunction, the AND operator between, and let me just highlight at this point what we are looking at. We are looking at this column and this column to get the AND decision. All right. So true, false gives a false. Remember that for the AND, everything is false except when both values are true. So true, false should give a false. True, true returns a true. True, false is a false, and false, true is a false. That's the third step completed. All right. And then we have to do the conditional part of it. However, before that, we have to find P. So there's no negation here. So we just copy the values of P from the first column to the last column here in step 4. And let me just highlight at this point with a different color which columns we are looking at. So here the AND values and the P values. All right, these two columns are being compared to get the conditional value. So again, for the conditional, the only time we will get false is when the if statement is true, but the then statement is a false. All right. So over here, FT resolves to a T. TT resolves to a T. FF resolves to a T. FF resolves to a T. So we do not have any situation, any case where the first one is a true and the next one is a false, correct? And that's why all of them resolve to a true statement, which is the last step. We write that below the condition symbol, and that is what makes it an implication. So yes, this is an implication. So the statement is a tautology, right? All the cases are true for the final value. So it is an implication, all right?